So let me get the slideshow started here. And yeah, no, I appreciate the opportunity to chat a little bit and tell you a little bit about the work we're doing. Some wonderful presentations and some really interesting things I've seen so far this morning, or at least this morning, California time. And I think Paul's presentation, there's a little bit of things you can see, right? The ability to measure and the ability to see things can tell you a lot. You sometimes need the data to be able to make decisions. So OndaVia, we use a Raman spectroscopy. Tell a little bit about how that works, but we use Raman for doing chemical analysis. We've spent last 15, 16 years growing capabilities, especially for the monitoring of process chemicals in the oil and gas sector. So Raman spectroscopy, jump into some of the background here. If you haven't done Raman, well, it's not surprising. It's probably something, if you took undergraduate chemistry, you spent maybe half a day talking a bit about it and then moved on. Raman is an old technique. It was first discovered, it's over 100, I think 105 years ago. Nobel Prize was awarded for it. But it has remained somewhat, let's say, esoteric. Up and through the 1990s, this was the type of stuff that was laboratory only. It was massive piece of equipment, size of a dining room table, lots of mirrors that would need adjustment. Student comes in the morning in a research group at a university and adjust a bunch of mirrors, and by lunchtime is ready to take a piece of data, and then off to lunch and back. And just before dinner, you get a little more data, and you slowly work through your graduate work. But what's happened over the last 15, 20 years is Raman has become much more portable and much more versatile. It's an optical technique. You take a laser, you hit a sample, hit a material, and you look at the light that comes back. Vast majority of light that comes back at the same color. But a few photons get absorbed and scatter off the material at a different color. And that change in color is information about the bonds in the material. Some bonds will be Raman active. They'll absorb a little bit of that light, and a photon will come back at a different color. And it allows you to fingerprint materials. It's often used in chemical identification. So we've seen these systems really being driven by what's done in optical telecom, go from being large benchtop, even larger scale instruments down to truly portable. That picture there is a portable Raman spectrometer that's actually at this point about 20 years old. That's even some old technology used by law enforcement, used by border customs for doing rapid identification of chemicals, used by hazmat. What chemical is in this 55-gallon drum? Rapid identification, quick check of materials. And because of that portability that's happened because of optical telecom, it allows us to start looking at applications in a more larger variety of industries. So OndaVia, what we do is take Raman spectroscopy and turn it from being a identification to being a quantitative technique. So starting about 15 years ago, we started to get calls out of the oil and gas sector. How can we measure this chemical? Here's a process chemical we're having trouble with. Do you have a way to measure this? We then moved into some more downstream applications, looking at trampoamines, for example. Can we identify these quickly on site or more easily in our lab? And have continued to build up a set of test kits and methods that enable rapid chemical analysis. And it consists of an instrument, which is a Raman spectrometer, and a test kit, which is a consumable. And combine those, turn Raman from being just a identification, a fingerprint, into being a true analytical grade quantitation method. To date, we've delivered systems all over the world. There are people using Raman for doing process control, process chemical analysis, everywhere from middle of the North Sea to under the ocean on a submarine, not oil and gas application, but submarine application in Australia. So wide variety of methods and applications and deployments. Okay, so let's talk a little bit about some of the things we do with Raman, some applications we see that really make quantitation, point out the importance of being able to quantify properly. And our first is to talk a little bit about a method that's typically done via titration. Right, so hydrogen sulfide scavengers. Obviously, dealing with any type of sour gas, sour oil, you're worried about hydrogen sulfide. And at a certain level, using scavengers versus an amine unit is a very powerful way to reduce your sulfide levels. Very common hydrogen sulfide scavenger is MEA trizene. 100 million metric tons are produced annually across the world. Very widely produced material, very easy to use for hydrogen sulfide scavenging. And it works by taking an MEA trizene molecule, as the ring structure shown here on the right. The theory is it takes two hydrogen sulfides, scavenges up those sulfurs, creates a dithiazine molecule, and some residual ethanolamine. And that sulfur is permanently trapped in the dithiazine, removed from your gas stream or from your oil, and now you've dropped your sulfide levels. Now, MEA trizene itself is a pretty, theoretically is a pretty simple molecule to make. You start with ethanolamine, MEA, and you add formaldehyde. 3 molecules of each. Theory, it's quite simple. You just, in fact, it's an exothermic reaction. You take 3 molecules of MEA, you mix with 3 molecules of formaldehyde, you'll get 1 molecule of MEA trizene and water. And if you do this properly, if you have pure materials to start with, you end up with 80% trizene, 20% water, and you're off to the races. So very simple in theory, but in practice, not so simple. The number of examples I have of where this can go wrong is quite surprising, and much of it driven by the fact that formaldehyde is the definition of formaldehyde can change depending on where you're buying it from. If you're getting a 37% formaldehyde, a formalin solution, it's stable in water, but it's 37%, not 100%. You can get a heated tanker of formaldehyde at 50%. That'll limit your trizene concentration, but it'll make a fine trizene. But again, you've got to do your math properly. Or you can go out and get paraformaldehyde. Again, 100% formaldehyde reacts quite nicely, except that you got to get the paraformaldehyde to dissolve. So that might require addition of a little base, might require some heat, require some mixing. All of these add a lot of to those that don't do the math properly can result in the wrong outcome and the wrong output. We a few months back received a sample. A customer called up, was having some trouble with their trizene. They're switching suppliers. They were getting an 80% trizene. COA said 80%. They're testing in their lab, so they were getting an 80% trizene. We measure it. It's a 20% trizene with 45% free MEA. And you say, well, how's that possible? Well, you go back and work out the math, and that's because they were using formalin, 37% formaldehyde. So the reaction wasn't going to completion. They're adding the right amount of amine, but not necessarily the right, well, in this case, not the right amount of formaldehyde to make an 80%. And this is because the methods for measuring trizene are, well, there's multiple methods, and many of them can be blind to the true trizene concentration. Titrations, very simple method, very easy to do, but they don't actually measure trizene. They measure amine content. Remember walking into a facility and sitting on their desk. They had basically the setup I show there on the left, a stir bar, and they were dropping hydrochloric acid in, watching the pH change. Of course, shockingly, not done in a fume hood. pH probe had never been calibrated. All types of questions about how they were making that work. But worse, if you to do a titration of an 80% trizene and a 75% trizene with 5% free MEA, you actually end up with the same endpoint. The titration measures the MEA content, not the trizene content. So trizene, when put in an acidic solution, hydrolyzes. It splits back into formaldehyde and MEA, and your titration just measures the MEA. To the point where I've said to customers, well, why are you even putting formaldehyde in? Just ship the MEA. You'll get the same result with a titration. And there's three vials there, three canning jars on the lower left of trizene that were delivered. One of those, customer expected 37%. We did some testing to help them out, found it was a 33% trizene. Titration, it's awfully close, very difficult to tell the difference between them. And it's really only 10%. So it fits within the range that they were putting on the COA. The problem is that 33% is 10% worse, which means they're changing the tower 10% more often, and they were throwing 10% of their money down the drain. So measurement is essential. And titrations can't tell you the true answer. Now, NIR, there are attempts to use NIR, and I get folks call all the time. Can we get some trizene? Can we get some other materials? Because we want to make an NIR curve. And trizenes are aqueous solutions. NIR is blinded by the water. So this is an NIR spectrum this is an IR spectrum of water. And you can see how the absorption due to the water has multiple peaks and begins to increase over the NIR range. So building a calibration curve using NIR leaves you blinded not only by the water, but variations in temperature and environment and lenses and focus and all types of other things that really make it challenging to use NIR for true quantitative analysis of MEA trizene. And then other methods like HPLC or GCMS, these high-end laboratory methods, yes, if you get a PhD chemist, they can do a fantastic job spending all the money you have in your budget to be able to do testing of this type. With HPLC, you've got serial dilutions to get within range and all the errors that come with it. And with GC, you're going to have to do complex derivatization because MEA trizene isn't a stable molecule, especially at low levels, and you're not going to be able to get a good analysis through your GC of trizene without doing very careful sample preparation and then dumping the money into those systems. And that's where we like using Raman spectroscopy because it sees all. Raman is water, does not have much of a Raman spectrum, so we can look at things in aqueous solution quickly, simply with an optical method and get results for not only MEA trizene, but all types of other aqueous oil field production chemicals. So here's some examples, example data of what it looks like in the Raman spectrum. On the left, we show a range of concentrations of MEA trizene. And at the bottom is the green trace that's flat is 0. It just includes an internal standard that allows us to reference. And then we increase the concentration. You can see how the spectrum increases. And then when passed through our software, it turns that data into a quantifiable result. And we get a calibration curve like shown on the right. This is a 2-minute test. You open an ampule, you add your sample, you put it in the instrument, click start, and you get your numbers. Instrument's portable, take it out in the field and get data very quickly. This is the power of Raman spectroscopy. It's optical, it's simple, and with appropriate calibration and careful forethought, you can build calibration curves and analyze chemicals in the field or in your lab simply, easily, and cheaply. But the fun part about Raman spectroscopy is that there's additional information in that spectrum. So here's MEA trizene and with some excess reagents. On the right, I show 3 different preparations. The green trace is just a 53% MEA trizene. The black trace is 44% with 8% free formaldehyde, and the blue is 46% with 13% excess MEA. And the spectra differ. The peak at 870 in this case is related to, let me see if try and find my little cursor here, but the peak at 870 is related to the MEA, and there's a peak that sits at about 910 that's related to formaldehyde. That information's in the spectrum. So now we can pull that information out and also be able to tell you how much is free formaldehyde, how much is excess MEA. Many folks, when producing MEA trizene, will leave some free MEA in the solution so that you don't end up with any free formaldehyde for safety and hazard reasons. So you might have 5% free MEA. That might be expected. But by using Raman, not only can you identify that and know the quality of the material, if you're producing MEA triazine, you can now optimize. You can get yourself down to 1 or 2% and really know you're there. And if you're buying it, you know kind of the quality and production capabilities of your vendors and suppliers. And this comes, in the end, if you're buying MEA triazine or if your chemical supplier is providing it and using it and putting it on site for you, knowing the true concentration allows you to optimize your process. If you get a COA, you might get a COA that just says something like conforms. What does conforms really mean? It means it fell within some range that your supplier has decided is going to work. You can have a triazine that's 10% off. And as we've seen, and the customer can find that, your gas rates are a little different, your sulfide's a little higher, and so we need to use a little more chemical this month. When really, if you do the true testing, you know the true concentration, and you can optimize your process around it. What makes Raman even more powerful is we can look at what happens in the spent triazine. Again, aqueous solutions, and Raman gives us the ability to look in those samples and identify materials that are present that really before have not been studied or considered, and allows us more process optimization than just looking at the inputs to the process. So again, pull this graph back up. MEA, so the theory behind triazine scavenging, get MEA triazine, 2 sulfides, you end up with a dithiazine and some ethanolamine. But in reality, this is a multi-step process. You start with triazine. The R here is just the ethanol group. 1 sulfur comes in and you get a molecule called thiodiazine, MEA thiodiazine. That precedes a 2nd sulfur shows up, the sulfide ends up and you create thiodiazine. And we've done this in our lab. This is actually, you can see on the bottom right there is an image of the bottle contains thiodiazine that is precipitated out. And the test tube at the end there is a little bit of a dithiazine as a oily kind of grayish liquid. For years, the theory, in fact, the published work has said thiodiazine is a very short-lived molecule. That work was done with NMR at very low concentrations. Low concentrations in that setup, it is a short-lived molecule. But if you really think a bubble tower, a contactor tower, and you're pushing gas through it, you're going to build up a huge amount of thiodiazine before you ever get to your dithiazine endpoint. And naturally, it's going to have to work that way. And we've seen in our lab work that the thiodiazine actually generates at a fairly high concentration before you ever end up with dithiazine. So being able to measure these molecules allows you to truly watch the reaction and know where problems occur. The problem with the dithiazine endpoint is that it forms solids. There's a picture there of, kind of the worst case endpoint where you're in with a jackhammer removing these solids. So we have customers that come to us and say, hey, look, we want to be able to measure this process. Can we monitor how much triazine we have remaining? Because we want to know when to change our tower. And I turn and say, well, actually, the problem is your dithiazine, because that's what forms the solids. So why do we measure dithiazine? In addition, thiodiazine, the in-between molecule, grows to a pretty significant concentration. So you really don't care about how much triazine is present. What you care, because much of it will be thiodiazine before it ever stops scavenging. The real problem is dithiazine. So can we find a way to measure that? What makes this even more interesting and more a challenging problem is it's a very complex mixture. There's water, triazine, thiodiazine, dithiazine, sometimes other solvents. You might have some methanol as antifreeze. You might have varying levels of H2S, CO2. Temperatures can change. Gas flow rates can change. Very complex mixture, which means that the outcomes and potential problems can vary very significantly. And so in the end, being able to measure, being able to monitor can give you insight into the process that just measuring breakthrough can't necessarily tell you. In addition, these are complicated because dithiazine is soluble in triazine, but not water. Triazine is soluble in dithiazine and soluble in water. Thiodizine, partially soluble in both. So mixtures can quickly lead to levels of phase separation. So here I show a sample of a spent scavenger on the left. The upper percentage of that bottle is basically a spent triazine solution. The bottom part is a phase separated dithiazine layer. At some point, that material that's mostly spent, some point that material moves to what you have on the right there, a bunch of solids that build up in your pipeline, on your, in your heat exchangers, and every other piece of equipment you have downstream. Because the dithiazine has because we're using Raman spectroscopy, we can look at those materials and quantify the individual components. So like we did before, MEA triazine has a very nice spectrum. Dithiazine is a completely different spectrum, and we can pick out the carbon sulfur peaks and say, can we quantify that material? Turns out we can quantify it quite well with Raman. That makes it so powerful. So when we measure a solution like this, what we find is that bottom layer is 80% dithiazine, plus or minus. Again, some variability on this, so lots of approximations, but 80% dithiazine, 20% triazine. The upper layers, mostly water with triazine, and some mostly thiodizine remains. Now, you could, if you let this settle, take off that upper layer, continue to use it. It's triazine and thiodizine. You can continue to scavenge with it, and you can throw the dithiazine layer out. But more importantly, what we have found, and again, this is in general terms, is that once that dithiazine reaches about 15% total mass volume, it phase separates, which is the point at which you start to worry about solids formation, because we can now get a layer of something that is very high concentration dithiazine. And that's the point at which nucleation event can occur, and now we can switch to solids. Being able to measure allows us to get insights into this process, and real time or even even frequent monitoring can give you that insight. But more, the solids are often, we get solids all the time. Folks will say, okay, do I have dithiazine? And we find that actually quite frequently, no, the solids are not dithiazine. Often we find that the solids are just a paraformaldehyde. It's formaldehyde that is built up. Or we've moved all the way to an elemental sulfur phase, and sometimes we truly have dithiazine. What's happening on the far left, how are you ending with formaldehyde? Well, folks worry about, they don't want to get solids. They don't want to get a dithiazine residual. So they overdose MEA triazine, run their budget up, add extra chemical, in the hope that they won't get to the 2-sulfur step. Well, that triazine, if it doesn't scavenge, hydrolyzes. So it hits water in the system, it splits into formaldehyde and MEA, and then eventually the formaldehyde concentration builds in the water to the point where it precipitates out as paraformaldehyde. So an attempt to avoid dithiazine solids actually ends up with formaldehyde solids forming instead. In other cases, the thiodizine and a mixture of that will build up, and as it precipitates out, the thiodizine breaks down, and you end up with just a residual of combination of multiple things, but it could just turn into effectively an elemental sulfur built into a polymer. And in other cases, you truly do get a dithiazine byproduct. So the process chemistry is complex, many different potential outcomes, and only by monitoring and measuring can you really control that process. When we look at quantitative Raman for hydrogen sulfide scavenger analysis in the field or in a process control application, we really generally say, look, monitor your dithiazine. This is the problem compound. As it starts to climb and it hits a certain level, that's the point at which you need to worry about changing something. If you want to avoid solids, watch for dithiazine, but you can also do things like monitoring for formaldehyde with Raman to be able to avoid overdosing and find that optimal point at which you can run the process without getting all the way to the end point, but finding that happy medium in the middle. And we are in the process of adding quantification of thiodiazine. Since we're able to produce the material, we can build calibration curves, and we are studying that now to be able to do a full suite, full analysis from triazine all the way through the endpoint of the reaction, all using Raman spectroscopy. So let's take a little bit of a right-hand turn and talk about something else, somewhat related to the sulfides, but a different process chemical. And in this case, I want to talk about biocides. So biocides, microbial control, essential part of oil and gas production chemistry, right? You need to sulfate-reducing bacteria, for example, well, find that sulfate, produce hydrogen sulfide. Locally that can release to MIC. You can get your local corrosion. If it really pushes to the endpoint, you can end up getting your bacteria in your whole formation to turn it from sweet to sour. So essential to provide the right amount of biocide to keep microorganisms from growing, but not overdosing your biocides to avoid environmental issues and a whole suite of other problems we'll talk about in a second. So the biocides I'm going to talk about here are THP-based biocides, THPS, THPC, becoming more widely used because they're considered green biocides. Their degradation products are generally safe. Both sulfate and chloride versions exist. They do create a bit of an environmental concern because they can release formaldehyde. So under basic conditions or even slightly neutral conditions, UV light, you can get formaldehyde release, which, depending on your regulator, can become a bit of an issue. But there are other biocides, quats, widely used in many different applications for biocide control, and then glutaraldehyde is another common biocide. So the goal with your microbial control is to provide enough, but not too much, right? Not only the environmental concerns like formaldehyde, but impacts on infrastructure. Some of these chemicals and maybe the solvents they're shipped with can cause issues of their own. Corrosion can affect gaskets, other failures. They may be incompatible with other chemicals you want to use in your system. And, if in the right situation, you can actually lead to superbugs that may be somewhat impervious to the materials you're dosing, which might require careful thought or careful changing of different biocides over time to make sure you don't form these. And of course, in the long run, you want to avoid overrunning your chemical budget, not just dumping biocides in and spending money. So the solution is to monitor for the biocide and really to watch your produced water, watch the water's coming back and decide, do I have enough biocide present? Is there some remaining, or am I putting too much in? And this is at the ppm or even preferably the ppb level. Now, you might say to me, look, hey, yeah, you're using Raman spectroscopy. Raman's a really neat technique for bulk percent level measurements, right? It's great for your plastics recycler to be able to say, is this, which plastic is this, right? Before I put it in the right bin. And that's true, down to even sub-percent level can be very challenging with normal Raman spectroscopy. And that's where we've pushed Raman forward using a technique called surface-enhanced Raman. This uses gold nanoparticles, a solution of gold nanoparticles that amplify the Raman signal. Academic work has shown this down to single molecule detection capabilities. For us, we look at it as a way to take Raman from, let's say, 1,000 ppm down to 10 ppb. Or 100 ppb, depending on the measurement. Now, SIRS, again, is an old technique. It's been around since discovered in the mid-70s, and you're likely not going to find many instruments out there that use SIRS because of its Achilles heels, reproducibility. Various variations in the system that can cause very large changes in the output. Basically, we have something that's an amplifier. A small change in the input leads to a very large change in the output. And so small variations in the environment can lead to errors on the output. And that's where our series technique, it's uses an isotope or other internal standard that allows us to turn surface-enhanced Raman spectroscopy into a commercially available quantitative analytical technique. And we do this for amines, and this is what we do for trampoamines in refining applications, for quats in food and bev applications, and for a variety of things in the oil and gas sector. Here we look at some data we have from trampoamine analysis. Over 2,000 data points, 5 years, 25 different spectrometers, dozens of different operators, and we get response and data that is pretty much equivalent to using an ion chromatograph for the same application at a fraction of the cost and complexity, all over the single calibration curve with an instrument you can take out in the field and do your analysis. So formaldehyde, talk about how we do aldehyde analysis because it relates to a lot of the biocides. That's a 3-step process. You mix your sample with a reagent, you wait, mix your sample with another reagent, you wait, you mix it with a third reagent and you test. It's about a 30-minute process, and you can do, in this case, I'm showing the graph here on the right shows ppb level formaldehyde analysis with great linearity. Very simple technique and shows the power of a single Raman instrument that can go from ppb level all the way up to the bulk percentage level measurement. It's also extremely specific to formaldehyde. So why is this relevant? Well, for THPS, THPS releases formaldehyde under the right conditions. One of the reasons that environmental concerns are raised, but we can leverage that to become an analytical method for THPS in real-world applications. So we just measure the formaldehyde with a THPS kit. So this is being done, in West Texas for doing THPC, various wells there, or being done offshore in the North Sea for monitoring flowback or produced water for their biocide concentrations. And here's actually a couple wells taken off that platform, monitoring of 2 different wells and the THPS concentration over time, over the course of a few days, and very easily able to pick up differences as is injected in one place and then look at different wells as it comes back and know what the concentration looks like. And this allows them to optimize and know we've got just enough, and when they're pushing too much, and be able to figure out if things are moving in strange ways within the formation to make sure that injections are happening properly and in the proper locations. The power of this, to come back to the power of Raman, allows us to do measurements from amines all the way through metals, for a wide variety of applications. And we've replaced dozens of complex capital-intensive laboratory instruments. Can be done with a single portable instrument. And for production chemistry, being able to get the data you need to make real decisions, real time on site, instead of shipping to a lab and waiting 72 hours, invaluable, because after 72 hours, data is meaningless. And I may have check the time here. Yeah, probably caught up a little bit of time. But yeah, would love to take any questions. Contact info's there if you've got some questions, but we don't want to put them online.
Well, thank you so much, Dr. Mark, for this great presentation. That's quite interesting about measuring the H2S scavenger concentration. That's something, as you mentioned, a lot of people suffer from because they just inject the chemical in their chemical tower. They think it's 100% working, but a lot of the times, like you said, it's not the actual actives that are in there. So this is going to be a game changer for a lot of operators and production chemists. Same thing goes for the biocides as well. If anybody have any questions for Dr. Mark, please go ahead and drop your questions in the chat box here. I'm also going to drop his contact information. This is his website and email address. If anyone interested in contacting him regarding his products, here's the contact information for everybody in the chat box. George is asking, can you handle MBO as well?
Yeah, great question. Yes, so in fact, we've built, we started with the MEA triazine, because the massive quantities are produced, but have continued to expand to doing MMA triazine. We're seeing a growing interest to that, and then MBO, or maybe could be considered a MIPA triazine if you wanted to. But yes, all 3 of them. able to do full suite analysis across not only the production side, but the spent side.
All right. I think there's another question. No, that was related to the previous one. Just a quick question from myself here. Let's say someone is taking a sample from the pipeline and he's taking it to the lab to do H2S scavenger analysis. How much changes in the actual actives of the H2S scavenger might happen during this time period? Let's say half hour, going all the way to the guy that's dropping the samples in the back of his truck, has to drive, I don't know, 70 miles to the lab. What can happen in that time frame?
The scavenging will continue. Yeah, so that's an interesting one. And one of the advantages of being able to do this right on the back of the truck, right? Take a system and, put tailgate down and do your data there. The thiodiazine molecule is somewhat unstable, so it will like to disproportionate into dithiazine and back into triazine, so it can push your numbers around a bit. And if I guess if you take your sample and you drop it on ice and do some things to preserve it, you can slow up that process. But I think if you're somewhere warm environment and driving around, you can continue scavenging, and your number's going to be off a bit.
Yes, yes, this is going to be a great impact as well on the process optimization. Another question. Hello, Dr. Mark. Can you tell me the recommended triazine ppm for each H2S ppm in gas liquid phases?
That's kind of complicated question. I have to think that through a bit. There's a lot of details there in terms of mixing and flow rates and such, right? So, I mean, theoretically, one triazine takes, two sulfides, so you can figure out your mass ratios. But, I think we've seen, okay, the ppm level is one thing, the percent level doing contact hours another. The mixing, the chemical engineering of the process, probably has a, in fact, I'm going to say probably has a more significant impact than the chemistry of the reaction, right? So, and by chemical engineering, I mean, what does your system look like, right? What are your flow rates? What are your CO2 and, water, other levels, other things that are present that can affect that reaction? What's the temperature? And what is the mixing like? So not sure I can answer that directly, but if someone send me an email, I'm happy to think through, some more specific details.
Yeah, like you mentioned, Dr. Mark, it's very, very complicated process because most of the time the H2S scavengers, whenever they inject it, they're probably between 40 to 80% actives. That doesn't it doesn't go like very good in molecular ratio. The second thing is the mixing, as you mentioned, because sometimes we have to inject using either like an atomizer or even to install a static mixer to improve the
Yep.
mixing a little bit because you're shooting a liquid and you want to make contact with the gas phase, and that's how difficult that is. So yeah, like you mentioned, it's actually more of trial and error. Sometimes it can
Yeah.
be 3 to 1, sometimes can be 15 to 1, depending on all of these factors.
Yeah.
All
And
right.
that's where we see the power of the measurement is, well, let's see what we have remaining, right? Let's go downstream and see how much triazine residual, how much dithiazine you have, how much thiod do we have, right? And get the true data, instead of either, waiting for breakthrough and wondering why we went 26 days instead of 30, or waiting till someone screams about having dithiazine in their pipeline.
Exactly, exactly. This is how normally that goes. Sometimes I've seen people either injecting water with the like in the gas line to just give it a little bit of solubility to avoid these solids building up in the pipeline. So yeah, it's adding this tool like measuring the actives of the H2S scavengers, besides of course measuring the H2S, that will be a game changer for a lot of operators for sure. All right, any more questions from anyone? I think that's probably it for the questions. Well, if anybody has any questions, I dropped Dr. Mark's contact information. I'm going to drop them again in here. Feel free to reach out to him, check his amazing products on his website. And many thanks, Dr. Mark, for this interesting session. I myself learned a lot from that. Hopefully to have you again, maybe in the coming event to talk, maybe to tell us another new technology that you are going to provide for us.